Hey folks, Dr. Cole here. Let's go on to the lecture ANOVA Part 2. So in the last lecture, we learned about the one-way and two-way ANOVA. What I taught you was called the between subjects ANOVAs. Now we're going to learn about the repeated measures ANOVA, and then we'll also practice a mixed design where we have a repeated and a between, or what they call a between within, because the repeated measure ANOVA is also called a within subjects ANOVA. So let's talk a bit more about the repeated measures and what we're talking about here. Repeated measure ANOVA is a type of analysis of variance used when the same participants, and that's where the word within subjects means. So the same participants are measured multiple times under different conditions or at different time points. So that's what within subjects means. We're not looking at male or female, which would be one set of observations for males and another set of observations for females. Here we have the same people who are measured at different time points or at multiple measures. And time here is just a a uh, uh, a referent to anything that is measured over multiple times in those people. It could be different doses, different times, etc. But typically we use the word time to help us understand that. So when we think of things happening in a time at different times, that's what describes a longitudinal design or a longitudinal study or experiments where participants are exposed to different conditions or treatments and their responses are measured. And so in contrast to a between subjects design, for example, a one-way ANOVA, which compares independent groups, males, females, etc., different factors, repeated measures ANOVA compares dependent groups, meaning go back to your paired samples t-test. So the repeated measures ANOVA is the equivalent of the paired samples t-test, where each group consists of the same participants measured multiple times. This design increases statistical power by controlling for individual differences because each participant serves as their own control. One thing I want to say that I haven't said yet is when we are talking about between subjects designs, the data are what we refer to as cross-sectional data. It's like one moment in time, a cross-section in time. We collect data from males and later we collect data from females, or we collect data from people who are, recall what we did last week, people who are employed at different levels. So each of them are considered cross sections. You can't be both an unemployed person and a full-time worker. So that's why the observations are different, and that's called cross-sectional data. In contrast with repeated measures data, we've got a situation where it's well suited for longitudinal data. Same people measured at multiple times, like we did a couple of weeks ago when we did the paired samples t-test. We have homes measured at one time in, let's say, the spring, and then longitudinally later on, we measure them again in the fall. All right, so when do we use repeated measures ANOVA? We use it when we have one dependent variable, a continuous variable such as test scores or anything that we're measures, and we have one or more within subjects factors. So that's where the within, because it's the same people within the same person. And that's our independent variable then, is the particular repeat. It could be time, it could be dose. So this is where the same participants are measured at multiple time points or under multiple conditions. So here's a scenario. Imagine you are conducting a study to test the effectiveness of a new therapy. You measure the participant's stress level at 3 time points. Before therapy, which might be called time 1, mid therapy, which might be called time 2, and after therapy, which might be called time 3. It really doesn't matter what we name the different time points or the different repeated measures as long as we're being consistent. And then this actually becomes, so the independent variable, and then in this case would be time, or it could be therapy. Doesn't matter. You'll see when we set it up in JASP how we are going to define a variable, an independent variable name, and then it will have different repeated measures levels. Just like in the between subjects designs where we had different levels, like I believe when we did income, we made 4 levels, right? And what we're looking for is to see if there are significant changes in the dependent variable, which is stress, over the levels of the repeated independent variable. So in this case, over time. All right, so key terms within subjects factor. That's our independent variable. The independent variable in a repeated measures design is the within subjects factor, where each participant is measured under every condition or at every time point. In the example, times within subject factor with 3 levels, time 1, time 2, time 3. So notice what we're saying. Within subjects, every participant is measured under every condition. So it's not that some people are measured at time 1 and other people are measured at time 2 and other people are measured at time 3. That would be a between subjects design. That would be a cross-sectional study. Here, this is a longitudinal study. Everybody is measured at the different time points. The dependent variable, that's our outcome. We're going to have one score. That's our score that's being measured at the different time points. And so in this example that we gave here, we're talking about the level of stress, whatever that self-report stress level is. Maybe that somebody is saying on a scale of 1 to 5, tell me what you are. They're completing a survey. Now, one of the concepts that we've been talking about when we think of assumptions, we've already talked about the assumption of normality because it's a parametric test. There's this assumption called sphericity, an important assumption in repeated measures ANOVA that the variances of the differences between all pairs of conditions, or for example, in this case, time points, are equal. So that's like saying when we had the different groups or the different levels of our between subjects that we were assuming similar variances. And we can control for this very easily in sphericity by just asking for the statistics to apply a correction called the greenhouse geyser is the most common. So again, assumptions, normality, sphericity, independence of observations, although the observations within subjects are obviously related because they come from the same participants. And the observations when we do between different subjects must be independent. Okay, so how repeated measures ANOVA works, just briefly. In a repeated measures design, the variance in the dependent variable is broken down into 2 components. So within subjects variance, this is the variance that comes from differences in the responses across the time points or conditions in the same participant. And any between subjects variance, the variance due to differences between participants. We're going to be doing, our first example is just a simple, what we might call simply a one-way repeated measure. So we're just looking at within subjects variance, and then what's left over from that becomes the leftover that's called the residual in the ANOVA. And then the second example we're going to do today is actually a within between. So we'll be looking at both of these variances. Okay. Now, what the repeated measures is doing, it's testing with whether the within subject factor explains a significant portion of the variance after controlling for any between subjects differences if we actually had another independent variable that was a between subjects variable. And like I said, we'll get to that in the second example today. Now, something about the way the data are organized. The terminology that's used in data regarding how data frames are set up is whether or not data are considered long or wide. Long and wide data formats are two common ways to structure your data set, especially in repeated measures and time series analyses. The choice of format depends on the type of analysis you are performing, the type of statistical software, etc., with each format offering its own advantages and limitations. JASP uses wide format. Wide format is also how SPSS works, and I believe Minitab uses long format. So in long format, each row of the data set represents a single observation, and multiple observations for the same subject are listed in multiple rows. Okay, so here's an example. So let's say we've got here 3 participants, right? This is called long data. So participant 1 measured at time 1 had a score of 80. The same participant at time 2 has a score of 60. So this is what we call long data. JASP doesn't work with long data. JASP needs wide data. So turning the long into wide would be like this. So now we have one participant, each participant has their own row, and it's like each variable is the different repeated measure, time 1, time 2, times 3, much like how you did the paired samples t-test. Remember, you had home price appraisal in the spring, home price appraisal in the fall, and each row is the same house. And then you just did the paired sample t-test of the 2 columns. Well, we're kind of doing that in repeated measures ANOVA, but in this case, since it's more than 2, we can't do a paired sample t-test. We're going to do a repeated measures ANOVA. Now, there's no easy way to change if your data are long to wide in JASP, but you can easily do that in Google Sheets. So we're going to practice that. And basically what you ended up doing is we're going to use something called pivot table, and then the rows become the participant or the ID, the columns become then the time, the repeated measures, and then the values, the scores that go into those cells under each repeated measure is whatever your dependent variable, whatever it was that you were measuring. In this example here, it would be stress, the stress level, right? So no longer do we see the word stress level when we go to wide. It just becomes the score that's being measured under each of the time points, and we just have to understand what we're doing. Now, just like in the between subjects ANOVA that we did last week, the 1-way and the 2-way, we want to conduct a post-hoc test after we conduct the ANOVA, particularly if we find any significance, so that we can see where the significance is. It may be that time 1 is different than time 2, but it's not different than time 3, but that's enough, because just like before, we're looking for anywhere that there's a difference. They don't all have to be different from each other. But whereas before we used the Tukey, now with repeated measures, the recommendation is to use a Bonferroni. And we'll get into that when we look at JASP. And Bonferroni is simple, a conservative method used to control the family-wise error rate, just like Tukey is controlling the family-wise error rate. When conducting multiple comparisons, it does this by adjusting the significance level, just like Tukey does, but Tukey is not preferred for repeated measures. So we'll get into that when we take a look at the results. Okay, so let's get into our first example. A 1-way repeated measures ANOVA, meaning just one independent variable that's we're measuring the same participants at. You could have a 2-way repeated measures. We're not going to practice that, but you could imagine that a person is measured at time 1 and they're given dose 1, and there's something that we we want to look at both of those because maybe there's something about time that is different in the world, not just that at that time one they got a particular amount of drug, and then at time two they got a different level of drug, but maybe it was time one was morning, and time two is afternoon, and time three is evening, and the same person gets measured morning, afternoon, evening. Well, that's one repeated measure independent variable. And then the second would be, well, then they're also getting different levels of a drug. In the morning, they're getting one dose. In the afternoon, they're getting a different dose. So that would be a two-way repeated measures ANOVA. We're just doing simple. And once you get it with one of these, it's through trial and error, you learn how to add in more variables. So let's look at this example scenario using the data frame Bush-Tucker food. So let's describe the data and then let's bring it into Google Sheets and take a look at what's going on. So this is a fictional data set, Bush-Tucker food, where we're measuring the number of seconds before celebrities retch while eating disgusting food. So each participant, which is a celebrity, is consuming 4 different kinds of disgusting foods, right? Everybody's eating all of the different foods. So it's repeated measures. Everybody's eating a stick insect. Everybody's eating a kangaroo testicle. Everybody's eating a fisheye. Everybody's eating a witchetty grub. And then we're measuring how much time until they throw up. And we want to find out, is there a difference across these animals? So the experimental question is, does seconds to retch change significantly over the food type? So our null hypothesis would be that the mean seconds is similar across the food type. That is, the type does not have an effect on retching. If we find the p-value is less than 0.05, then we reject the null hypothesis. We infer the alternative hypothesis, H1. At least one of those foods has a different retch time, right? There's at least one significant difference in the mean retch time between the food types. So that's as if we were saying type does have a significant effect on retching. Okay, so let's go ahead and look at the data. Okay, so we see from this that these data are, oh, by the way, I'm doing it in my Google Drive, so I'm already able to open it right in Google Sheets. And so I'm going to open it right now in Google Sheets. Remember what we're doing, because I'm not giving you edit access to the drive that this is in. You have to download the file and then open it up in your own Google Drive. So this is what it looks like in Google Drive. And you can see this is long data, right? We have participants there. We don't have one participant per row. So we have to turn this into wide data before we can analyze it in JASP. So here's how we do it. First, you highlight the data. Okay, so this is all the data we want to pivot. We're going to do insert pivot table. And we want to put the pivot table in a new sheet so that we can then have an ability to then save this as a new CSV file that would then be imported into JASP. So the first thing that pops up is some suggestions, because it's thinking that you might want some sums or some totals or some averages, which are also things you can do in pivot table. But we're just using pivot table to just reorganize the data. So just click on this little arrow here, we don't want the suggestions anymore. And what we want to do is we want to say, we want the celebrity or the ID or the participant, right? Whatever this first column is, which usually is going to be ID or celebrity, and you need to have that. You need to have a column. If you only had the attribute, you're going to have to make a column that has identifiers so that the pivot table knows how to keep things organized. So the celebrity is really our ID. So that's now going to become the row. See now, so we just have one ID per row. We're not needing to show any totals, so we'll uncheck that. And then the columns is now going to be what was listed here as the attribute or the food type. So now we're turning the data wide. So each celebrity will have the seconds, the amount of time it took them to retch, which is the score is seconds. That'll go here. And we don't need to show this grand total at the end here. We're just formatting the data. And then the values are our value, which just happened to have been named value. It could have been named seconds. It says value. And so those are our scores. Okay, so we can close this now. So now we have the data. It's ready to go. The only thing is it's a pivot table. So we need to just copy the data, because at this point, since it's a pivot table, you can't just delete row one. You could hide it, but if you download it as a CSV, it's still going to be there. So the easiest thing to do is just copy your data, Control C or copy, create a new sheet, paste in that data, and now we've turned, right, the long data into wide data. And these are each of the repeated measures, because every celebrity eats all four of the animals or the food types. And then our scores here are how long did it take for them to retch, right? So we could double check. So celebrity one, fisheye, it took 1 second. Well, in the original data, yes, celebrity one, fisheye took 1 second. Celebrity two, stick insect took 9 seconds. So we'll come over here. Celebrity two, stick insect 9 seconds. So it does it right. And you're good to go. And now you can download this CSV. And now we can open up JASP. And we can import the data, which are now properly formatted as wide data. So here it is, the Bush Tucker food. And now we can analyze it. And you can see that it is basically leaving as interval data, which is correct. If we wanted to, we could change each of these, like fisheye, we could change them all to continuous variables. But ordinal is essentially a continuous variable. Ordinal and scale are continuous variables, whereas nominal is your categorical or factor variable. So it wouldn't have mattered. We didn't need to do this, but I just want to do it because I kind of like us having some consistency and helping you understand that these are continuous variable, number of seconds. So now we're ready to do the analysis. So let's just jump right in and go to the repeated measures ANOVA, and let me start teaching you how to do this. So we want to name our independent variable. The dependent variable is already the seconds, right? The dependent variable is each score here. That's really the dependent variable. That's the number of seconds. So now the independent variable becomes whatever this independent variable name is that we want to say. Well, these are all different animals. So we can, if we want, we can call this animal or food type. Why don't we just call it food type? Let's call it animal because these are animals, right? Animal. And then level one of this independent variable is going to be fish. That was one animal. Level 2 is kangaroo. We add another level, stick. And then one more is grub, right? So those are we've now named the levels. And now we actually then have to align the repeated measure cells. What's the analysis going to be? So you can see we have our 4. And I was using the tab key, by the way, to tab through these. Okay. So we put our we now start lining them up, and we bring them in. So fish eye is the variable that is the level name for animal called fish. Could have called it anything. We could have called this animal 1, animal 2, animal 3, animal 4, but it's good to have the names because it's easy to follow along. And then kangaroo will go here, and stick will go here, and grub will go here. So now we've put in all of the levels of our independent variable, and then the repeated measures runs. The ANOVA can now run because that's what it's looking for. Now, what do we see? We see that sphericity was violated, so we need to correct for that. Since we're here, we might as well add in, like before, the 8s squared. Pretty real big effect. So lots of difference. Somewhere there's a pretty big effect for this different food type. We need to come down here to the not the model, assumption checks. And so what we're going to do is we're just going to correct. Let's use the Greenheiser. So what we will report, and by the way, since it was violated, we don't really need the none anymore. We're just going to be reporting the greenhouse, so we can get rid of the none. And all we're going to report is the Greenheiser. You can see the degrees of freedom are slightly tweaked, whereas before it was a whole number, 3 and 21. After the correction, it becomes 1.5 and 11.18, and that's how you report it. We would report those. We will report F for 1.6, 1.59, comma 11.18 equals 3.79. P equals 0.062. So it's interesting. In the absence of the correction, we have a significant effect. But because we had that violation, now let's look at the Hund. Okay, so here the Hundfeld correction, which is also appropriate, gives us a statistically significant. So let's go ahead and use that one. Remember, we use statistics. Statistics don't use us. So we are left with a statistically significant finding, P less than 0.05. We have used an appropriate correction to address this violation of sphericity. And there's no output in the between subjects effects because we don't have a between subjects variable, and that's okay. Now what we can do is we can do the post hoc test. So we're going to bring in animal, and we're going to ask for the Bonferroni, and let's flag and letter, and then we will see what do we have here. So we have fish and kangaroo are not different, but fish and kangaroo are different than stick. So really stick is the one that pops out, right? Stick is different than fish, and stick is different than kangaroo. So when we plot that out, now we'll be able to see what we have here. And I think that's everything that we need to do. Now we'll do the descriptive plot. So animal on the x-axis. Let's make sure we add in the error bars. We'll do the standard error is what I like. There we go. And I believe we need, do we need to click on normalize error bar? No, I guess we don't need to click on normalize error bar, just standard error. And yeah, now we can see that no difference between fish and kangaroo, and stick is different than those two. But stick is not different than grub because there's just enough variability in grub and stick that there's, the post-hoc test did not find a significant difference between stick and grub, right? But we see here the P with the Bonferroni correction is less than 0.05 for fish being different than stick and for kangaroo being different than stick. And that is it. So good to go. How do we write that up? Let's add a note. Results of repeated measures, ANOVA, found a significant effect of animal type on seconds to retch, colon F 1.99. It's basically 2. We could round it off to 2, that's fine. 2 comma 14, because 13.98 is basically 14. That's fine too. Equals 3.79. So probably we want to, before I finish that, we want to say results of a repeated measures ANOVA with HUYNH-FELD correction found. Okay. P equals 0.048. Remember, less than 0.05, so it is statistically significant. Eta squared equals 0.35, which is a large effect. And then post-hoc tests with Bonferroni correction found, then maybe it would be specifically post-hoc test with Bonferroni correction found stick, the, what is it, the insect stick insect animal type had significantly longer retch time, significantly longer time to retch than either the fish or kangaroo. Right? Longer, more time. This is time, right? So we can also fix this, come over here to edit image, give a label to the y-axis, right? It needs a label. This is the seconds to retch, right? Seconds to retch. So longer time. Stick was the least the least distressing, right? Fish and kangaroo had the most uncomfortable taste that led to retching. So I think we're good to go. This would be a good, probably a good finish to the assignment. Show all of this. I don't think there's anything else that I want to suggest you bring in there. There's other things you can practice and play around with, and you're always welcome to add more things to your output if you want to learn about them. You could do very interesting rain cloud plots of your data just to show What do the raw, what is the distribution of the data? What do the actual data points look like? Um, I'm not asking to do that, but that's a very, very cool graph. I love this graph. I think that's good to go. Okay, so let's move on to the next example. We just did that one. Okay. A mixed design. This is our final example. Um, and then you can do your assignment. All right, so this is a mixed design. What does mixed mean? Between, within. I explained that before. So this is used when your experimental design includes both a between subjects factor or factors, variables where different participants are assigned to different groups or conditions, and within subjects factors, repeated measures, variables where the same participants are measured multiple times under different conditions or at different time points. This combination of between subjects and within subject factors makes the mixed design ANOVA particularly useful for studies where you're interested in both group differences and changes over time or conditions with the same participants. So here you have a situation where you have one or more between subjects factors, so different groups, right? Those are independent observations. So what does that mean, independent? Well, you can't be a male and a female. So this might be like, we're going to look at all of the male celebrities and see if those differ in their retch time compared to female celebrities. Okay. And that's in fact what we have here. So let's go ahead and look at the data and let's bring it into Google Sheets. And so you see we have long data. We can't bring this into JASP. We're going to have to convert this to wide format, but we can kind of see what's going on. So we have celebrity one is a male, and they're measured across the 4 animals, etc. So celebrities 1 through 8 are males, and now we have a whole nother group, different group of celebrities. 9 through 16 are females. So once we fix the data, we can take a look not only within subjects, how are all of the respondents, how are all of the celebrities retching, how much time does it take for them to retch across the animals? But then we can see, is there a difference between males and females? Okay. Now I wanted to just show you, because I'm thinking that the word value might have confused you, because pivot table has the word value. Let's change this to seconds, just so that you can see what's going on here. Okay. So let's highlight our data. Boom. And now we're going to insert the pivot table, new sheet, create the new sheet with the pivot table, collapse this. Now you see seconds is that variable, and that goes under values. So let's start with first by going, the celebrity is a row, but also we've got to put in the fact that the celebrities are also organized by their gender. So that's going to go also under row as well. So, right. So we've got that's now aligned the celebrity and it's put in gender. I think we could have put, let me double check something. I wonder, could we have put that under, we maybe could have put that under as a column. No, because see, it's making it why we don't want that. We need the column to be, gender needs to be one factor. So in fact, yes, gender does need to go as a row underneath celebrity and unclick the totals. So now gender becomes its own independent variable. And now then we just do what we had done before. Under columns, it's going to be the attribute. In this case, that was the food type. And then under values, that's our seconds. That's our dependent variable, the seconds to retch. So now this is now correctly formatted wide, where we'll be able to bring each of these animal types as levels in our repeated measure independent variable. And then now gender can become a between subjects factor. So let's grab this data, copy, put it in a new sheet, and then now download this as a CSV, and then go to JASP, open, bring in some new data from the downloads folder. There it is right here, bush with the gender. And you can see it's importing, and now we have correctly formatted data, right? Gender is a nominal data. It's a factor. It's ready to be a between subjects factor. Then let's get started. Repeated measures. So let's start with the repeated measures. Again, this is our animal. And again, we've got, what do we got? Fish, tab, kangaroo, tab, stick, insect, tab, grub. Okay, let's fill in the cells then. Fish, kangaroo, stick, grub. And that's everything that we did before. It's different statistics though, right? Because it's a different data set. But we see it's still violated the sphericity. So we'll come down here. We want the eta squared and the assumption checks. Let's take a look at, does any, we'll do them both and see if there's any difference. Not much of a difference. And then now what we want to do is add the between subjects factor. So that's gender now becomes the between subject factor. And now we can get the results for that. And you can see here, we don't need to be correcting for sphericity with that. So I would say that it probably doesn't matter too much whether we use the greenhouse or the hunt. Sticking with what we did before, why don't we use the HF correction? All right, so looking at this, what do we see? Well, we have a main effect, just like before. We had a main effect for the repeated measures of an animal. We have a between subjects effect for gender, because that's less than 0.05, but we don't have an interaction between the within between, right? Nothing about different genders is impacting how they're responding to the animals, except that overall there's a difference. And let's go ahead and then, since there's no significant interaction, we don't need that post hoc test. But let's do again for animal, just so that we have that available. I mean, you're welcome to put in the gender, but it's just going to be the same thing as the test, because there it is. It's just two of them. Flag, letter, descriptive plots will do. Horizontal will be the animal. How about separate lines for gender? Let's do error bars, standard error. And one last thing while that's running. Okay, we can widen this out so we see the animals. There we go. So we see there's that between subjects difference, right? Males retch quicker than females. This is all hypothetical data, by the way. I made it up. Now, one thing we can do is to get an idea of how much difference in the overall seconds is there between males and females. We can look at this marginal mean. Marginal is like it's estimating. So if we put in gender, we'll see here down at the bottom a table. So it's saying that it's estimating that on average Females have about 6.6 seconds. So there's about a 1 second difference between females and males. That's what marginal means gives us. Okay. And there's really no reason to do marginal means for the interaction because there was no significant interaction. If you just wanted to see the marginal means for the animals, you can see, regardless of whether they're males and females, it was the stick that we see right in our display. The stick has the longest. So regardless of whether you're male or female, it takes about 8.6 seconds to throw up when you eat a stick insect. So maybe tie all that into some interesting notes. For example, results of a mixed design, repeated, let's see, what are we calling it? I think it's just called a mixed design. Let's go back and take a look at what I say in my notes here. Yeah, mixed design ANOVA. Results of a mixed, oops, results of a mixed design ANOVA found a significant main effect for animal and or we could say significant main effects for animal and gender, but not an interaction. But there was no significant interaction, period. No significant interaction was found. And again, report all the Fs. I'm just going quickly here. Report all the Fs. Maybe you want to say specifically there was approximately a 1 second difference between males and females, right? And other things that you might want to say, stick was the longest, right? Eating the stick insect led to the longest time to retch, approximately, what was it? 8.63 seconds. 8.63 seconds, etc. Okay, I'll take a look at we'll take a look at what you're writing and grade it appropriately. So that's all that we're doing this week. Those two examples and just two questions on the assignment this week that are appropriate for this. Good luck. Thank you. Bye-bye.